So let's get started. To start things off, please join me in welcoming Sean, who works with NCWSC, and he'll be introducing the speaker today. Go ahead, Sean.
Great, thanks. Hopefully you can hear me. Well, it's my pleasure today to introduce Jacob LaFontaine, who's a hydrologist at our Norcross, Georgia office of the USGS, and he's part of the South Atlantic Water Science Center there. His project work over the past several years is focused on the development of hydrologic models in the southeastern U.S. He's worked done interdisciplinary work on the modeling of watershed systems project in that region, and he's also worked a lot with different programs in the survey and our partners, such as the National Research Program here at USGS, my program, the National Climate Change Wildlife Science Center, also the National Water Census, our DOI, Southeast Climate Science Center, and then Gulf Coast Plains and Ozarks LCC and the South Atlantic LCC. Across all of that work, his research goals are primarily focused on improving the simulation of hydrologic processes at the conterminous U.S. scale. And he's going to be talking about his work today. It's my pleasure to introduce Jacob. Welcome.
Okay, thank you, Sean. It's good to be here today, and thank you everyone for signing in to watch this presentation as we share some of the work that we've been doing over the past few years, and we'll have some initial results as well as some other things that are still in process, and look forward to sharing that with you. So just an overview, we want to look to talk today about our hydrologic research objectives in this work and how that'll tie into the bigger picture that we see. Then focus on this regional application in the southeastern U.S., which is primarily in the Gulf Coastal Plains and Ozarks LCC, but we were able to expand the area with some additional funds from the Southeast Climate Science Center. And then I want to go to the bigger picture and talk about the National Hydrologic Model, which is something that's really made a lot of this work possible at this scale for us. So our primary research objectives, number one, provide useful information, hydrologic information to resource managers. We develop these simulations so that hopefully folks will be able to use this and incorporate it in their decision-making process on the ground across the landscape. Number two, what Sean had mentioned in my research goals, is looking to improve our understanding of the hydrologic system and also improve our simulation tools and applications. And so in this framework of hydrologic models that we work, some are very simplistic, others more complex, but we're never fully able to represent the natural system, but we try to, continue to develop the code to incorporate other things that we see as important hydrologic features in those simulations. So to give a historical perspective, so in the past someone may have developed a watershed model, and it may have been for perhaps a smaller watershed that maybe had a USGS stream gauge at the outlet, or even a smaller scale, or it was just a one-off research watershed where you had collected perhaps streamflow data and you wanted to start looking at simulations against that. Over the past, I would say definitely things have really ramped up in the past decade or two, when instead of moving, just doing one small application and that being the study, folks are looking at broader scales and finer resolution, and wanting more information at more finer spatial discretization and in a consistent way. And I think that's one of the things and the challenges in developing these larger models, is now that you have this huge framework, this huge amount of modeling units, you have information, streamflow information at certain places, but you may not have it at others, and how do you develop your model to be consistent? And so there was a lot of work done over the past 15 years as part of the Predictions in Ungaged Basins project, and they're really looking at, how do we get from where we have information to then say something useful about places that we don't have information, or maybe some place that has streamflow information, but it's affected by water management or water use or some other mechanism or process. And so we see these increasing size of the applications from, say, a watershed scale, maybe it's a couple hundred square kilometers, to then going to larger basins like past work we've done, the Apalachicola, Chattahoochee, Flint, that's about 20,000 square miles, to then something this size, that's maybe a couple 100,000 square miles, and then eventually leading to the conterminous United States. And so this picture here is out of a report by Julie Kiang and others. She's with USGS in Reston, and the red boundary represents our study area, so that includes the GCPO, LCC, as well as some areas, some watersheds to the east of it. And the blue shaded areas represent coverage by USGS stream gauges where those watersheds are deemed minimally impacted by anthropogenic effects. And so seeing that there's a lot of white area there and trying to get at perhaps what the system is without all the impairments as a starting point, we need to develop methodologies to provide water availability information in those ungauged areas. So looking at the regional application, that primarily is the work that's covered here today. The Gulf Coastal Plains and Ozarks LCC, this is a map of the landscape conservation cooperatives, and then the Department of Interior Climate Science Centers are bounded by these lines here, but the colored areas are the LCCs, and so we are, right here is the GCPO LCC, and so you can see by the previous figure, we have that included as well as the remains of the Tennessee River Basin, as well as some basins in most of Georgia. And so the project objective for this study was to provide an automated methodology and then resulting data products of hydrologic simulations. And so we can always, those that have done hydrologic models, you know that you can continually to tweak and adjust your model parameters to try and match a certain stream gauge. But once you've done that and you've adjusted it so much that it may be relevant at that place, but you may not be able to say anything meaningful at a larger scale or outside of that area. And so what we're trying to do in this work is provide a multi-model synthesis where we not only look at what each model may output, so there's 3 different modeling methods that are used in this study. There's a monthly water balance model, a daily time step hydrologic model called the Precipitation Runoff Modeling System, or PRMS, and then also statistical methods using Krieging and some nearest neighbor applications. And so what we look to do, instead of just picking a model and saying, all right, this is the one we're going to use, we're trying to synthesize different methods to inform the other so that we end up with a better product that's a combination of those efforts. And the products are primarily looking at flow characteristics across the landscape and in the stream network, and also looking at current or historical and future climate drivers, as well as land cover attributes. And some of this information is actually currently hosted on a web portal that I'll give a brief demonstration within the presentation. I'm not going to be bold enough to do a live demo, that's for sure. So we'll get to those slides here shortly. So the study area for this project, so in the GCPO LCC, this region is very diverse. It's just over 250,000 square miles. It touches or includes parts of 12 different states in the southeastern U.S., and it has 5 different subgeographies, from interior highlands to the Mississippi alluvial valley, the coastal plain, as well as the Gulf Coast. And so just within this area, getting much different hydrologic response depending where you are, and different drivers and potential anthropogenic impacts across that area as well. And so just to give you some of the background information about the landscape in this area. So the top left graph is elevation range across the basin. So you see a lot of the coastal plain is, less than 50 or 100 meters. The highest elevations are in the southern Appalachians and the Tennessee River Basin. When we look at dominant cover type or land cover type, we see the majority is covered by trees or a forest environment, but there are some areas where it's grasses or perhaps agriculture. And then when you look at more of the wetlands and shrubby areas by the coast, but not as much bare land cover type, which would predominantly be seen in urban areas. When we look at impervious area, we see that the reddest areas are the most urban, and so we see Houston, Texas, pop up, and we see metropolitan Atlanta and some other metro areas across the region. And then another aspect that we also look at is what we call depression storage, and so these are the off-main stem water bodies. So they may be farm ponds or just wetlands or natural features, or you could be looking at small municipal reservoirs. And so trying to look at how those also impact the landscape, and we see that by and large most of the study area does not have a lot of these depression storage features, especially in the northern part. But once you start to get into the coastal plain, then you start to see the percentages of the modeling units really represented by these features. When we look at the climate inputs for temperature here and precipitation to come across the area, you see by season that here in the cool season we see probably the biggest ranges of gradients of temperature from the coast on up to the interior, basically tracking with latitude. But when we get to the summer, we see that it's relatively uniform across the area for that, and then in the fall again kind of mimicking the winter. And so each of these things is going to play into different parts of the water budget and how the hydrologic response happens. When we look at the same seasonal breakdown for precipitation, and these averages are for the historical period from 1949 to 2010. We see that the northwestern part of the study area definitely seeing smaller precipitation accumulations in the winter as well as the fall. And then you see that the coast really has the larger share of the precipitation distribution in the summertime. And so all of these things changing over season as well as over the landscape that need to be incorporated in these simulations. So looking at our input climate data sets, for the historical climate data, we are using, it's a gridded product for the country, for the conterminous United States. It's on a 12-kilometer by 12-kilometer grid. It was developed by Ed Maurer and others. And it's a daily time step product of temperature and precipitation from 1949 to 2010. We're able to access this information and summarize it to our modeling units through the USGS Geo Data Portal, which the URL is provided up here. And so pretty much over the last several years, we've been using this tool to provide inputs of climate to our hydrologic models. It definitely makes that process more efficient, and then since these are developed for the country, makes it more consistent in that application. And so the nice thing here is if you have a GIS file of your model units, you can upload that to the GeoData Portal, and then it'll reprocess the gridded products to your polygons. So I encourage you, if you're looking for input data, to check out that as a potential source, because there's all kinds of information on there. For the future climate data sets, we focused on both CMIP3 and CMIP5. Some of the results that I'll show today for the monthly water balance model are a combination of the both, and then for the daily model, there's some CMIP5 results. And so these are daily time step from 1950 to 2005 is a training period, or the historical period, that they were statistically downscaled from the general circulation models to the Maurer data, so that we could then use them as input to our hydrologic models. And there's a range of in the CMIP3, there were emission scenarios, so different levels of forcings and how that would impact temperatures and precipitation over time. And now with the CMIP5, they've changed to representative concentration pathways, but still meant to provide you some scenarios based on what could happen in the future. One thing that we've incorporated since we're doing these long-term simulations from 1950 to 2100, that we know that land cover characteristics do not remain the same, and so we needed to address how that impacts our modeling and our simulations. And so there's a product that was developed by Terry Soule up at Eros in South Dakota, and they developed an annual time series, an annual land cover change product from 1940 through 2100. And so it has these these classes up here on the left-hand side. So not as detailed as perhaps like National Land Cover Data Set, but still providing a range of categories. And so I'll just scroll through some decadal changes in the Southeast here from 1940. And so you can see that in 1950, you start to see some of the large reservoirs showing up in the Southeast. Into the 70s, you perhaps see some of the urban areas start to grow. One thing that I did notice, as you start to get later, you start to perhaps see a greening of the landscape, or perhaps things that were hay and pasture or cropland were perhaps regrowing, or new growth forests. And so then we get to kind of current conditions here at 2010, and then as we project forward in the decades up to 2100, you see all the urban areas start to grow, and perhaps some of the cropland areas starting to come back as crops in the future. And so if you want further information on the development of those, definitely see that URL for that product by Terry Soule. And so here's now the current conditions versus the end of the simulations, and just how the changes in urban and even going from forest to a grass or an agriculture would have impacts on the hydrologic response. And so in the models, we look at, things like impervious area or dominant land cover type, or interception by the vegetation canopy as things that could be adjusted to reflect some of those impacts. And so looking at our application of the monthly water balance model, and so this is a relatively much more less parameter based model than PRMS, the daily time step. So water balance model has, I believe, 5 input parameters and 7 output variables, and looks at monthly temperature and precipitation, and how that interacts with the landscape, and has various storages in the soil zone, and computes runoff. And so when this was developed for actually the country in cooperation with EPA, as well as the South Central Climate Science Center, as well as this project that we were working on with GCPO and the Southeast CSC, we have this national scale model of the monthly water balance model currently running, and that was developed by Andy Bach and others with the National Research Program. And so I won't go into the details of calibration and things, so we can share some results, but I'd definitely be happy to have offline conversations about more details than that if folks are interested. But this looks at just some performance metrics. So Nash-Sutcliffe Index, or the NSE metric, is one of those that's used to measure the hydrologic performance, simulation performance. And so anything that's 0.6 and above, we feel fairly confident about that simulating the hydrologic time series. And so we see for the Southeast, and especially for our study area, that the monthly water balance model is representing fairly well the broad range conditions in the Southeast study area. And so this was part of the regionalized parameterization. And then these 2 maps on the right-hand side looked at actual individual stream gauges and the calibrations of those. And so we see that larger amounts, when you're just targeting a stream gauge, you're able to match even better. But then once you're over here in regionalizing, there's some trade-offs to fitting all of the stream gauges at the same time. And so here's some output from those model runs. So the water balance model was developed for the conterminous United States, and then they used 214 downscale general circulation model inputs that were downloaded from the Geo Data Portal, and were run through 2100. And so this analysis by Greg McCabe and others looks at a synthesis of all of those runs and how we see changes in temperature and precipitation and runoff into the future at the 2030, 2060, and 2090 time slices, and those are with a period of record that's averaged around those. So that's the average, the averaging year. And so the P25, well, the P50 represents the median of those simulations, what the change in temperature is. The P25 is the lower part of the middle part of the distribution. So you got the 25th percentile, the 50th percentile, and the 75th percentile of response. And so I'll blow these up for you so that you can get a better look at what that means for the GCPO area. And so here we have changes in temperature at the 2030 year, and so we see, based on the right-hand side, that in the GCPO, it's either some warming, perhaps, just over 2 degrees, but then if you look at the lower end of the range, it could be less than that, or if you believe the higher. And so we definitely get a range of not much to perhaps, over 3 degrees C. Then when you start to go 2060, you see that, further progressing, as then a lot of the runs are showing a tighter range as we go into the future. And some of this, and the fact that we have large areas of dark red, is that the scale tends to top out at about 5 degrees C, so a lot of these may be different than that, but are lumped together. And so we see by 2090, those changes are further away from zero. When we look at precipitation, it doesn't tell as clear of a story. So the same percentiles of the 214 GCM runs, and looking at those breakpoints to capture the middle 50% of how the models are simulating this response. And so for precipitation, for 2030, you could either be a bit below what we see now, or we could be above what we see now. And so that tends to be the case for each of these time slices. And so, if we're below zero on the percent on the departure in millimeters, or if we're up around plus 20 millimeters of departure. And then even in 2090, we still see this range that either goes plus or minus. And so, being in the southeast, that we're, our hydrologic response tends to track, with the precipitation. We see that runoff has these, the same type of response, where it could be drier or it could be wetter, depending on the realization of the GCM, of the downscale GCMs, and which ones we select for our area, or if you take the whole range and you plan accordingly for potential increases or decreases. So, seeing wintertime on the lower part near the Gulf Coast, you may see some larger departures in the negative direction for accumulations, but at the upper end, you could be above zero. So definitely makes it tougher for the managers to have to say, well, which way is it, when we're not changing in the same direction over this range, but instead you could be plus or minus. It definitely plays havoc with how you plan. And so this is just a summary plot of all those individual slides that we just showed. So this is being published by Greg McCabe and others, and so it's in draft now, and so we look for that to be available soon. But all the information that went into making these is available. The water balance model results are hosted on this portal at this URL here on the page. And so through this web portal, you're able to access the water balance model outputs at each of the response units that makes up the national model, each of the stream segments that makes up the national model, and then you can either get the data, the raw data out, the simulated data out, or you can get some what we've coded as options to get figures and graphs and things like that. So I'll just run through this. So from this initial screen, you would go in and you could pick the graphics option up here, and then once you zoom in far enough, the stream network will start to show up in the hydrologic response units, as well as the stream gauges that are available. And so you can pick your local unit. So right here, a hydrologic response unit is selected. Or if you pick a stream segment here, then it will give you the entire catchment that's above, that drains to that stream segment outlet. And so just selecting an HRU here, you go and you pick, your local HRU. This is the ID. This is the variable that is selected, so average temperature. Then looks at the start and end range, and then you can pick all the runs of the historical temperature and precipitation, forced or the GCM-based simulations. and then get a plot out like this where it's monthly temperature based on that 19-year period, and looking at the prism-based simulations in the blue, or looking at other historical products like DayMet or the Mauer grids, or looking at CMIP5 or CMIP3. And you can save these out, or again, save the data that made these plots. So switching to the precipitation runoff modeling system, which is the daily time step hydrologic model. So here's a schematic of it. So more boxes, more processes represented than the water balance model. And so each of these boxes here represents a different piece of the hydrologic cycle. And for some of these, there's multiple options to where you can simulate different types of, potentially evapotranspiration methods or things like that. And so this the model takes inputs of precipitation and temperature and computes the hydrologic response across the landscape with plant canopy, snowpack if you're in an area that builds a snowpack, impervious area, the soil zone, looking at depression storage features on the surface, and then the groundwater reservoir. And then on the right-hand side is where we have all the different flow components that are output from each of those different conceptual reservoirs on a daily time step. And so for the GCPO, this gives you an idea of the density of the stream network for this hydrologic model. So this entire area, including the GCPO, LCC, as well as the area to the east, is just over 1 million square kilometers in size. Out of the National Hydrologic Model, we extracted 20,251 hydrologic response units. Their areas are about on the same scale. If you're familiar with the hydrologic unit codes, about 12. With stream network connecting those HRUs of just over 10,000, just over 1,000 stream gauges that we can either look at comparing information or using for model calibration. And then because we have a regional model, and of course it's at the outlet of the Mississippi River Basin, we didn't have the resources to simulate everything above, upstream of this area, or we'd end up doing like a third of the country. So we, for the large rivers that flow into this area, we picked intersections with the study area boundary, and then you can use flow replacements at those to keep the main stem flows. But a lot of the advantage of this study is that, is looking at what happens in the tributaries, and so those aren't dependent on so much on what happens on these main stems. And so it's depending on the questions you're looking to answer, there's a way to get at both types of flow. So for the regional application of PRMS, what the stakeholders were really looking for here were statistics based on the streamflow time series that they could use based on historical conditions, and then looking into the future as well. And so in order to determine which statistics we could have some confidence in, once we computed them, that they represented similar distributions using the historical Mauer-based inputs, as well as the downscale global general circulation model driven simulations. Our methodology was to look at the historical records for the Mauer-based simulations and the historical record of the GCM-based simulations, and see if when we compute these streamflow statistics, do we get similar distributions? Now we know that they're not going to produce the same flows on the same days in the historical time series, but computing these metrics on an annual time step and then looking at the distribution of those 55 different values across the historical period between the two. And we use Kolmogorov-Smirnov test to see if those distributions are similar or dissimilar. And so there's 4 main categories of these statistics that we had settled on with the technical advisory team with the GCPO. And so we looked at a set that were for magnitude, duration, frequency, and timing. And so looking at a subset of the magnitude statistics, so looking at long-term monthly flows across the GCPO, and for each of the 12 months, as well as looking at a base flow index. And so for each of these plots, there were 22 general circulation models that were used in this study. So they may each have had a bunch of the representative concentration pathways, but they all have a historical period for training. And so we looked at how many of those GCM-based simulations match the distributions of the Maurer-based simulations. And so red means that none of the simulations match the Maurer, or up to 22 with the blue means that they all had similar distributions of these statistics in the historical. And so for the monthly periods, we see that, for the winter months, we see a lot more blue, larger blue areas across the study area. But when we start to get into the spring, and especially in the summer, we perhaps see there's difficulty in maintaining that similarity across the two types of simulations. And so whether that's a matter of types of storms, and whether it's frontal storms in the wintertime and convective storms in the summer, or some other driver that's causing these departures from matching the distributions, that's something to consider. The base flow index, looking at that base flow contribution from the groundwater, we see on the western side of the study area not matching as well as perhaps the eastern side of the study area. When we look at duration, again, looking at the daily flow, these running means of the high flows and low flows, we see the low flows do a fairly good job, but then when we see the high flows on the short duration, again, having trouble matching the short duration storm flows. Frequency, so this is the number of days in a year that's below the 25th percentile of the 55-year record. So some years will have more or less, and seeing that we definitely on the edges, the fringes of the study area and by the coast, perhaps trouble areas, and then for high flows, again, we see larger areas of dissimilarity. Looking at annual maximum and minimum flow date, what date did the minimum occur or the maximum occur, we see fairly good agreement across the GCMs and the Maurer-based simulations. But then when we start to look at rate of change, so the rate of change from in the positive direction or the negative, or the number of switches from positive change to negative change over the basin, we see that the Maurer and the GCM-based are not matching well. So our next steps on that work are to complete the PRMS simulations with the future climate and land cover. That's something I wish we'd have been able to get for you to see today. I'm glad we had the monthly water balance model, but that's coming in the near future to have those results as well. And also providing those statistics as well as some indication, not official guidance, but some kind of indication as to how we feel the models represent those various statistics of flow. And so this work was all made possible through the time and the effort that have been put into developing the USGS National Hydrologic Model. And so this was the Modeling and Watershed Systems group out of Denver and the National Research Program, so headed by Lauren Hay, have looked at developing this model at the conterminous United States scale at a reasonable spatial resolution as a starting point for assessing how do our models perform, are there certain things we need to address in parameterization or optimization or in the model structure itself. And so looking at each of these characteristics, and then bringing in anthropogenic effects, what types, it's the quality and quantity of the input data that we're using either to drive the models or to calibrate or evaluate the models. And then it becomes an issue of data management and, having gigabytes upon terabytes of information that will, need to be stored or presented in a way that can be accessed, and keeping folks being able to work on these projects, and so in long term, and so a lot of times folks are able to have opportunities to do shorter time periods to do a specific task, but looking to have some continuity as well to keep these efforts developing. And then computer infrastructure. I mean, we see the big leaps we've had in technology, and that a lot of that's enabled us to start running models at this scale, but along with that comes a cost. So this triangle really represents, the three big things. So we want the NHM to be nationally consistent, but locally informed, and then also stakeholder relevant. We want this to be something that folks will actually be able to use in their processes. So the NHM is set up with two models currently, PRMS and the monthly water balance model. It's based on the geospatial fabric, which is based off the NHD Plus version 1 GIS information. And so it was developed by the MOES project, and it took the regions, the NHD regions, and took all of these catchments and flow lines, of which, for this example region, are over 200,000 apiece, and boiled it down to something that's manageable and that we can run and we can test and improve the various parts of the NHM, the 7,300 HRUs and 4,000 segments. And so this was done for the country. We ended up with about 110,000 hydrologic response units that make up this model. All the input climate data, of course, are accessed from the Geo Data Portal. And I will say, and then calibration and parameter transfer are things that we're in process with now to look at, having something that is usable in the near future for folks. All right, at my peril, I will offer this out. So we do have a form with the modeling watershed systems. We do have a help form if folks are looking to use these software or they're looking to get started. We do have a set of recordings on this page to where they're all YouTube videos on the USGS channel that you can go see how the various pieces of PRMS work and get some instructions on starting up with that. But on this help box here is it goes to what is a help form if you have questions, but it also has a spot where if you want to model extraction from the NHM for PRMS, we can provide that. So it's the initial set of parameters. It's not calibrated, but it provides you a quick access to a reasonable space for resolution where you could have a functioning PRMS model with which to go on your project. And so here's what the form looks like. So it asks for basin outlet ID, also the upstream cutoff if you're only looking for, like we did for the GCPO, and application details. And so right now, we're working on an automated way to provide information, but right now it's pretty much it's me. And so you fill this form out, and I get the form, and then I go do the extraction for you and can send it to you. So like I said, at my peril, hopefully, for better or worse, if it results in a whole bunch of requests, then that's good, but that only makes us get the automated thing running faster. And so the NHM extractions will come with a fully functioning PRMS model for your basin, uncalibrated but fully parameterized. It's driven with daymet climate forcings from the period 1980 to 2014. And then you also get GIS shapefiles of the model hydrologic response units and stream segments so that you'll have some way to display information, your results, as well as your input parameters for those extractions. So the next steps for the NHM is to look at continental domain parameter estimation. So a lot of the lessons we're learning in this application and the GCPO will get to transfer out to those other areas. Of course, looking, it seems like every time somebody wants an application, a lot of times they need a finer resolution in a certain part, or they need to add a certain feature. And so looking at an automated way that we could subset or overlay a finer resolution, say like NHD high-res. Routing mechanisms at this national scale when you've got large rivers that may be gaining or losing or may have large impoundments and how to deal with those. Water use information, very important. I think with the National Water Census, we're getting a lot of that to, a lot of the states are able to put the water use information at site-specific locations into databases so that perhaps there'll be a more systematic way to then apply those to modeling units. Land cover change, again, if we see increases in urbanization, changes from forest to agriculture or other things, wanting to know how that affects water availability and eventually, stream flow statistics. And also stream temperature. So the SN temp model has been written into the PRMS code, And so along with streamflow and other parts of the water budget that PRMS simulates, you would also be able to get daily temperature time series at each segment. Supporting tools, so the Geo Data Portal has just been invaluable to us over the past 5-6 years since it has gotten started, and it's only, it's been very valuable in saving time about preparing the input data, especially for climate. The Core Science Systems folks, we've worked with them on their supercluster high-speed computing cluster out in Denver. And so this definitely provides, when we're starting to talk about 110,000 response units and being able to break that simulation out across multiple processors so that it's not all just taking forever, but you're able to actually simulate things in a reasonable time. A lot of collaborators going into this effort between the different models as well as the portal development and all of these things that eventually, this will be able to be all in, a lot of this information will be on accessed through Sciencebase or through the GCPO's Planning Atlas, all these ways to access this information as opposed to perhaps it sitting, on a hard drive somewhere or an FTP site. And I just want to acknowledge all these folks, most of them USGS, playing a role in developing different input data sets to these models, the models themselves, the parameterizations, processing the outputs. I just want to thank all these folks in this effort, and definitely the Modeling Watershed Systems Group, the GCPO, and the Southeast Climate Science Center, as well as other agencies such as like EPA and South Central Climate Science Center on the water balance model. And so with that, take any questions that you may have. I've put my email address up here, and also this is the link to the Modeling Watershed Systems page to where you could access the recordings or the help form.
Okay, thank you, Jacob. We do actually have a question already in the box, but if people have questions, feel free to enter them in the chat box as we're addressing these. But first we have a question. Could you elaborate on NHM development, and are you anticipating a similar modeling effect effort nationally? Sorry. Any schedule for other regions? He's in the Pacific Northwest.
Yep, so currently the National Hydrologic Model is set up for the conterminous United States. So the base level parameterization that we used for the GCPO is available for the country, and so it would just be a matter, so we've done more work to do calibration on the GCPO, but the starting parameters are available for every region of the country. And so if you're looking to obtain those, just go to the help form, and we can talk about which area you would need those for, but those are all available now. We look to have, further develop as far as doing the parameter estimation for the country this summer. And so I think the target is really to have the first, version 1 that has some parameter estimation beyond the initial parameters by the end of the fiscal year. So that would be like an NHM PRMS version 1.
Okay. And did the MWBM include alterations, or is all natural flow? Are the NSE values reported for reference gauges only?
So it does not include any alterations at this point. I believe there's some work that Andy Bach was doing to address looking at areas that, based on how the water balance model did and how the streamflow time series are looking at impacts to to streamflow. And the NSEs are for all the gauges, so it's not just the reference gauges. So back in that figure, you saw the large swath down the middle of the country, like in the Great Plains, that didn't do well at all. And so we're looking to, part of our work, this summer is looking at what can we do to address that.
Okay, and we have another two-part question. Will the data just from the USGS gauging stations be limited in this project? And could the hydrologic data from long-term agricultural research service and forest service experimental stations to capture rural basins hydrology? I'm assuming it's come from long term.
So I guess as far as perhaps getting time series at those locations, if that's the way I'm understanding, it would just be a matter of finding in the stream network in the national model or, in the GCPO application, which stream segment that stream gauge is on. If it's, it's not a USGS stream gauge. Those, we only have included USGS stream gauges in the model files, but if the NHM is at a fine enough spatial resolution that the drainage area is about the same as your stations, then you could extract that time series out of the model, perhaps to have that alongside your record.
Okay. Let's see. Looks like Paul's typing away. While a few people are continue typing, I do want to thank Jacob, and I want to thank USGS and NCCWSC and all the other partners that we have in this continuing webinar series. We do have a question real quick. Can these results be linked into stream stats?
I think that would be the way. When I was working with stream stats in the past, it seemed like it was maybe they've moved to more national consistent now, but it seemed like every state kind of had its suite of different statistics or time series that it included. But this could be just another option that perhaps it could be linked to, a time series. It's nothing that perhaps stream stats would compute on the fly, but it could be another data set that could be included. I don't see why that wouldn't be possible. Now, in addition, there is development on a national water census portal, and that will also be a way, and I believe the folks that house the Geo Data Portal also will be hosting that, and that will be a place where a lot of these nationally available time series will get hosted.
Okay, and will the model be able to handle the flow transport in tidally influenced rivers and streams in lower coastal plain?
So right now it doesn't address that type of condition. I think there are some folks in Florida actually that are looking to address that specific thing. And so it may be that something is developed over the relatively near time future, but right now the routing mechanisms are pretty much aggregate the flow that comes out the landscape and route it out of the area. It doesn't consider tidal effects. So we're going to look for those enhancements in the future.
Okay, and it looks like we don't have any other questions on the chat box, so I'd like to thank everyone who participated, and I'd like to thank Jacob once again, and be on the lookout for the next webinar in this series, and be on the lookout for the recording of this webinar. So thank you.
Thank you.